Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be drifting through the dark, mysterious depths of outer space and discovering one of the strangest phenomena in our universe. Void galaxies exist in total isolation, in regions of space so vast and empty that it's hard to comprehend. They're like remote desert islands floating through a sea of endless darkness. Most galaxies exist in groups. They cluster, collide, and affect each other through light and gravity. But void galaxies are different. They shine in immense expanses of nothingness, where neighbors are few and where the familiar bustle of the universe seems to fall away. And yet, these lonely galaxies are not lifeless. They spin, they grow, they form stars, and they carry on in places that seem almost too empty to hold anything at all. Tonight, we'll wander into that astonishing emptiness and explore what it means for a galaxy to survive on the farthest edges of space. We'll glimpse hidden structures, strange signals, and the vast unseen forces that shape the universe. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is get comfortable. Let your body soften and allow your breathing to slow. And as the day begins to gently fade away, join me as we explore these rare galaxies together. Let's begin. Void galaxies live where the universe is eerily almost empty. In most directions, there is almost nothing nearby to answer them. Our own galaxy belongs to a busy arrangement of neighbors, satellite galaxies, and long streams of matter. These systems do not. They inhabit enormous cosmic hollows called voids, where the distance between one substantial galaxy and the next can become astonishing. That emptiness is not a poetic exaggeration. It is a measurable feature of the large-scale universe, mapped by surveys that reveal great walls, filaments, and between them, immense underfilled regions. To find a galaxy shining in one of those vast hollows feels almost uncanny, like finding a lighthouse in a desert with no sea. And yet these places are real. They tell us the universe is not spread out evenly, but arranged in a grand pattern of crowded knots and deep gaps. Some galaxies are born not in the bustle, but in the loneliest terrain imaginable. Some galaxies drift millions of light years away from any crowd. If you stood inside one of these remote systems and looked outward with impossible eyes, the wider universe would feel far less crowded than it does from the Milky Way. We live in a region threaded with nearby galaxies, including Andromeda, the Magellanic Clouds, and countless dwarfs bound to larger structures. In a void, the nearest substantial company can lie millions of light years away. That is distance on a scale so large, it almost stops meaning anything human. Light itself takes ages to cross it. Gravity works across it, but patiently, weakly, and over immense spans of time. A lonely galaxy in such a region may spend billions of years without the kind of close encounter that can twist a disk, trigger a major merger, or fling stars into chaos. It is not merely far from a neighbor. It is living in a version of the cosmos where company has become an exception instead of the rule. Cosmic voids are the largest lonely structures we have ever found. Planets can be isolated. Stars can wander. Even galaxies can end up in sparse neighborhoods. But voids are larger than all of those ideas put together. They're among the greatest structures in the known universe, spanning tens or even hundreds of millions of light years. These are not objects you could point to like a planet or a comet. They are absences with shape, regions where matter is far thinner than average, because gravity has pulled more material into filaments, clusters, and walls around the edges. In maps of the cosmos, they appear like vast bubbles between brighter strands, giving the universe a texture almost like foam. Their scale is what makes them so astonishing. A single void can swallow distances that would contain countless ordinary galactic neighborhoods. When astronomers study one remote galaxy inside such a realm, they are not just studying a lone island. They are studying life inside one of the biggest emptinesses nature has ever made. A void galaxy can shine inside a darkness bigger than imagination. That contrast is part of what makes these systems so mesmerizing. A galaxy is already an extravagant thing, full of stars, gas, dust, dark matter, ancient light, and often a black hole at its heart. To place such a structure inside an enormous, underdense region changes the emotional scale of it completely. The light becomes more dramatic because the surrounding emptiness is so profound. It is like seeing a city glowing where almost no roads lead. From far away, the galaxy still looks ordinary enough through a telescope, perhaps a blue spiral or an irregular smudge. But when astronomers place it in its true setting, the context becomes astonishing. Around it lies a region where matter is scarce on scales too large for instinct to grasp. The galaxy does not stop being a galaxy, but it starts to feel like a survivor, a bright concentration of order suspended in a realm where the universe has left much of the canvas nearly untouched. These galaxies grew up with far fewer collisions than most others. That matters because collisions and close encounters help write the life story of many galaxies. In crowded environments, galaxies pull on one another, steal gas, stir up star formation, distort spiral arms, and sometimes merge completely into larger systems. Those violent interactions are one of the great engines of galactic change. But in emptier regions, that pressure eases. A remote system can spend much longer evolving without being shoved, shredded, or transformed by a major neighbor. Its disk may remain cleaner. Its motions may preserve older patterns. Its supply of gas may last longer because it has not been stripped away by a dense environment. This does not mean nothing ever happens. Small companions can still arrive, and internal processes can still drive dramatic change. But the overall biography is often gentler. Studying such systems lets astronomers ask a beautiful question. What does a galaxy become when much of the universe simply leaves it alone for billions of years? Void galaxies help reveal what the universe looks like without interference. They are useful for the same reason a quiet room reveals sounds that a busy street would drown out. In crowded clusters, galaxies are constantly influenced by their surroundings. Hot gas can strip away their fuel. Neighbors can distort their shapes. Repeated encounters can stir starbursts, feed central black holes, or shut down star formation altogether. In sparse regions, many of those external pressures are weaker or rarer. That gives astronomers a clearer chance to study what a galaxy does under more peaceful conditions. Its structure, color, gas content, and star-forming behavior may reflect a slower and less interrupted history. This does not make such a system simple. Internal gravity, feedback from stars, and hidden dark matter still shape everything it becomes. But the environmental noise is reduced. That is why these remote systems matter so much. They help researchers ask which galactic traits are fundamental and which are scars left by a busier neighborhood that never arrived. Some of them keep forming stars in places that seem almost abandoned. That is one of the most surprising things about them. You might expect a galaxy in an underfilled region to look old, dim, and exhausted, as though the emptiness around it had starved it of possibility. Yet many show signs of ongoing star formation, often glowing with the bluish light of younger stellar populations. The reason is that what matters most is not whether the wider region is empty, but whether the galaxy still holds enough cold gas to keep making stars. Some do. They preserve reservoirs of hydrogen that can collapse into new generations of suns long after galaxies in harsher environments have lost part of their fuel. In that sense, remoteness can be protective. With fewer disruptive encounters and less stripping by dense surroundings, a galaxy may continue building stars at a steady pace. So even in a place that sounds deserted on the grandest scale, stellar nurseries can still flare into life, proving emptiness does not always mean inactivity. The space around the void galaxy can span astonishing distances in silence. Not silence in the earthly sense, because sound cannot travel through that near vacuum, but silence as a kind of cosmic absence. There are fewer luminous neighbors, fewer obvious landmarks, and vastly more underfilled darkness between one structure and the next. The region is not truly empty. Thin gas still drifts there. Dark matter still shapes the landscape. Ancient radiation from the early universe still passes through it. Yet compared with richer environments, the contrast is stark. Imagine a bright vessel crossing a sea so broad that even another distant light becomes rare. That is the feeling these settings evoke in astronomers who map them. The emptiness is not just scenery. It changes how gravity gathers matter over time, how galaxies move, and how structures grow around the edges. A lone system in such a place becomes a marker for the size of the gap itself. By locating the light, astronomers begin to measure the dark expanse that surrounds it. To study void galaxies is to study loneliness on a cosmic scale. That loneliness is scientific, not sentimental, and it opens extraordinary questions. What kind of galaxy forms when the universe gives it fewer neighbors, fewer collisions, and fewer chances to be reshaped from the outside? What survives in that setting, and what never develops at all? Researchers use these remote systems to test ideas about dark matter, gas accretion, dwarf galaxy formation, and the growth of large-scale structure across cosmic time. In other words, a lonely galaxy can tell us something about the architecture of the entire universe. It can reveal where matter flowed, where it failed to gather, and how gravity sculpted both the crowded regions and the hollow ones between them. There is something astonishing in that. One remote island of stars, quietly turning in an immense, underfilled region, becomes a clue to the biggest pattern of all. Its isolation does not make it marginal. It makes it one of the clearest witnesses we have. A cosmic void is not nothing, but it is startlingly close. The word void sounds final, as though these regions were blank holes torn through reality. They are not. A cosmic void still contains matter, radiation, gravity, and the faint leftover glow of the early universe. What makes it extraordinary is the shortage. Compared with most of space, very little gathered there. Galaxies are sparse. Gas is thin. The familiar bustle of the cosmos falls away. That is what makes these regions so uncanny. They are not empty, like a room after the furniture is gone. They are empty like an entire landscape with only a few faraway lights. Astronomers trace them by noticing where galaxies fail to appear, and the missing pattern turns out to be huge, structured, and real. Once you understand that a void is not simple absence, but a place where matter mostly missed its chance to come together, the idea becomes far stranger. It is almost nothing on the grandest scale we know. Void galaxies often sit on faint hidden threads of the cosmic web. Even the loneliest galaxies are rarely floating at random. The universe is arranged in a colossal network called the cosmic web, where matter gathers into filaments, walls and clusters, leaving wide, underfilled regions between them. Inside a void, that web does not disappear completely. It becomes thinner, paler, and much harder to trace. Some remote galaxies seem to sit along these delicate internal strands, like a few beads left hanging on nearly invisible wire. That detail changes everything. It means the emptiest parts of the cosmos are not featureless deserts. They still contain structure, only in a much fainter form. Those subtle threads may guide thin streams of gas across immense distances, helping a lonely galaxy survive where it otherwise might have run out of fuel long ago. So when astronomers find one of these isolated systems, they are not just seeing a galaxy. They may be catching a glimpse of one of the faintest surviving lines in the universe. Even the emptiest voids still contain dark matter shaping what survives. If you could somehow erase every star and every glowing cloud, the deeper architecture would still remain. Dark matter does not shine, yet its gravity helps decide where galaxies can form and where they cannot. In a void, there is less of it than in richer regions, but there is not none. That hidden mass is one reason a lonely galaxy can exist at all. A remote system still needs an unseen halo to gather gas, hold stars in orbit, and keep itself from flying apart. This gives voids a special power in astronomy. They let researchers study what the universe can build when the invisible scaffolding is thin and the supply of matter is limited. A galaxy inside such a place is not only beautiful, it is improbable. It tells us that even where the cosmos seems to have neglected construction, gravity still managed to gather enough material to light a small island of stars inside a sea of scarcity. Many void galaxies are smaller, bluer, and richer in gas. That combination is one of the clearest clues that environment matters. Smaller often means a galaxy did not bulk itself up through repeated major mergers. Bluer usually points to younger stars, because hot newborn stars shine with a cooler-colored light before they burn out. Richer in gas means the raw material for future stars is still there, waiting in reserve. Put those pieces together, and a picture begins to form. Many of these remote systems seem to have lived slower, less crowded lives than galaxies in dense groups and clusters. They have often kept their fuel for longer, and that lets them continue forming stars, while other places in the universe have already grown quieter. They are not simple or unfinished. They are revealing. They show what can happen when a galaxy is given time, space, and fewer violent interruptions. In a way, their blue glow is the visible sign of patience written into the structure of the cosmos. Their quiet surroundings can preserve clues, erased in crowded regions. Busy environments are rough on memory. In dense clusters and rich groups, galaxies tug on one another, lose gas to help surroundings, and get repeatedly stirred until old traces are blurred or destroyed. A sparse region can be kinder to history. A remote system may hold on to cleaner rotation, more extended gas, and subtler patterns in its stars than a similar galaxy living in a crowd. That makes these lonely systems valuable to astronomers because they can preserve records that busier neighborhoods tend to overwrite. It is a little like finding an old manuscript in a dry cave instead of a damp city cellar. The information survives because fewer forces kept damaging it. In that sense, emptiness becomes an archive. It does not freeze a galaxy in time, but it can leave more of the older handwriting visible. When scientists read those preserved patterns, they get a rarer look at how galaxies grow when outside disruption is reduced. In the emptiest regions, a single galaxy can seem impossibly isolated. The word isolated sounds mild until you understand the scale involved. On Earth, isolation means a cabin in the woods or an island in the sea. In cosmology, it can mean a luminous structure containing billions of stars, yet still sitting in a region where the surrounding matter is astonishingly sparse for tens of millions of light-years. Some of these systems are not merely on the edge of a void. They sit deep within it, far from the richer filaments where galaxies usually gather. That makes them valuable and strange. Astronomers can compare them with similar galaxies in crowded settings and begin to separate what comes from internal physics from what comes from external disturbance. The result is almost like a controlled experiment written across the sky. A single remote galaxy becomes more than a distant object. It becomes evidence that even in the deepest underfilled parts of the cosmos, gravity still managed to gather enough matter to build something luminous, structured, and enduring. Some void galaxies may have evolved with fewer galactic scars. A galaxy can carry the marks of a rough life. Warped disks, torn tails of stars, missing gas, swollen halos, and distorted shapes can all hint at old encounters and long gravitational bullying. In a crowded region, those marks pile up. Close passes are more common. Mergers happen more often. Even near misses can leave lasting damage. In a void, many of those external blows are rarer. That means some remote galaxies may have spent billions of years avoiding the worst of the cosmic traffic. They still change, of course. Stars explode, gas clouds collapse, and internal structures grow and fade. But the large outer form may stay less battered. That is scientifically precious. A galaxy with fewer obvious wounds can reveal which features arise naturally from its own gravity and star formation, and which ones usually need a hostile neighborhood to appear. Sometimes the absence of scars tells a deeper story than the scars themselves, because it shows what the universe builds when it interferes less. Void galaxies can rotate peacefully without frequent gravitational harassment nearby. Galaxies are not static ornaments. They're vast rotating systems, with stars and gas moving in grand patterns that can remain orderly for immense stretches of time. In crowded regions, that order is constantly at risk. Passing neighbors tug at disks, stir asymmetries, and inject chaos into what might otherwise be a graceful rotation. In a void, the situation can be very different. A galaxy may keep its spinning structure for longer because there are fewer intruders to jostle it. That long mechanical calm can preserve thin disks, subtle spiral patterns, and extended gas layers that would be easier to disturb elsewhere. There is something almost startling about that. A wheel of billions of stars can turn through deep time in one of the loneliest environments in existence, not because gravity is absent, but because outside interruptions are rare. In those cases, isolation becomes a kind of protection, allowing motion to remain elegant across epochs almost beyond imagination. Astronomers use them to test how environment changes galactic destiny. This is one of the deepest questions in galaxy science. If two galaxies begin with similar ingredients, how much does their neighborhood decide what they eventually become? Place one in a dense cluster full of hot gas and close encounters, and place the other in a vast, underfilled region with only distant company, and their futures may diverge dramatically. That is why remote systems matter so much. They serve as comparison cases written into the sky itself. Astronomers can study whether their stars form at different rates, whether their gas lasts longer, whether their shapes remain calmer, and whether their central black holes grow under gentler conditions. In effect, the universe has performed a natural experiment across billions of years. A lonely galaxy becomes more than an isolated curiosity. It becomes evidence in a much bigger investigation about what comes from mass, what comes from internal physics, and what comes from the influence of neighbors pressing in from every side. A galaxy in a void may grow slowly, but not simply. It is tempting to imagine a remote galaxy living a quiet and uncomplicated life, as though fewer neighbors must mean fewer twists in the story. The truth is more interesting than that. Slower growth does not mean a simple history. Gas can still arrive along thin structures. Small companions can still appear after ages of darkness. Internal instabilities can rearrange stars, build bars, and trigger bursts of new formation. Even the feedback from young stars can heat and push gas around, changing the galaxy from within. What a void really changes is the balance of forces. External disruption becomes rarer, so subtle influences have more room to shape the final result. That makes these systems fascinating to study. They are not stripped-down versions of ordinary galaxies. They are fully complex worlds, evolving under a different set of pressures. Their biographies may be slower and calmer in places, but they are still full of turns, delays, surprises, and long-hidden consequences. These lonely systems can still host black holes, stars, and storms. Isolation does not make a galaxy dull. Inside many remote systems, the same drama found in busier parts of the universe can still unfold. Cold clouds collapse into stars. Massive suns live fast and die violently in supernova. Gas swirls inward and can awaken a central black hole, turning the core into a bright and turbulent engine. Magnetic fields thread through the interstellar medium. Shockwaves race across space. In other words, a galaxy may be lonely only in the large-scale map of the universe. Internally, it can remain a place of relentless activity. That contrast is part of the wonder. A system can sit in a vast, underfilled region with almost no nearby company, yet still contain its own fireworks, weather, and hidden violence. Solitude exists at one scale and chaos at another. A void changes the neighborhood around a galaxy, but it does not switch off the powerful processes unfolding inside its stars, gas clouds, and dark central heart. Some void galaxies look delicate because fewer encounters disturb their disks. A spiral disk can seem almost fragile, like something drawn from smoke and light. Yet those broad rotating structures are real arrangements of stars, dust, and gas, and they can be damaged by repeated interactions. In crowded regions, close passes and minor collisions often thicken disks, warp them, or blur their graceful patterns. In a void, some galaxies appear to have avoided much of that rough treatment. Their disks can remain thinner, cleaner, and more extended, as though the usual cosmic traffic never arrived to scuff the surface. That appearance is not just beautiful, it is informative. A delicate-looking system may preserve evidence of how disks settle, how spiral structure persists, and how star formation spreads when external jolts are rarer. So the elegance of these galaxies is part of the science. What looks serene through a telescope may be the visible result of billions of years spent in a neighborhood where the universe interfered less often and with a lighter hand. Others seem oddly warped, proving isolation does not guarantee calm. This is where the story becomes more surprising. You might expect a galaxy in deep emptiness to look especially tidy, yet some do not. Their gas disks bend. Their outer stars seem lopsided. Their shapes hint at disturbances that feel strangely out of place in such sparse surroundings. That tells astronomers something important. A quiet environment does not forbid drama. A small merger, an off-center inflow of gas, or a long-delayed encounter with a faint companion can still leave visible marks. In fact, those marks may stand out more clearly precisely because the background is calmer. There are fewer competing disturbances to muddy the trail. A warped remote galaxy therefore becomes a mystery worth pursuing. It asks what hidden event managed to bend a system that seemed to live so far from trouble. In that sense, emptiness sharpens the question. It does not erase complexity. It makes the clues harder to dismiss and often more fascinating to interpret. Void galaxies can still merge, though the meetings are rarer. Even in the emptiest neighborhoods, galaxies do not live under a permanent rule of solitude. Small companions can still orbit, drift inward, and eventually combine with a larger system. The difference is timing. In rich clusters and busy groups, mergers are part of the regular rough life of galaxies. In a void, they are less common and often involve much smaller partners. That rarity makes them especially revealing. When a remote galaxy shows shells of stars, faint tidal features, or a sudden burst of activity near its center, astronomers can sometimes trace those signs back to a rare encounter that changed the whole course of its tower. History. One quiet system can spend billions of years evolving slowly, then absorb a companion and emerge altered. That is part of what makes these galaxies so captivating. Their stories may unfold at a gentler pace, but they are not free from turning points. Even the loneliest parts of the universe still allow sudden meetings that reshape the future. Their star birth can continue long after busier galaxies grow quieter. In dense regions, galaxies often lose their fuel earlier. Hot surrounding gas can strip away their colder reservoirs, and repeated interactions can speed up the exhaustion of what remains. Over time, many of those systems turn redder and calmer because the raw material for making new stars has dwindled. A remote galaxy can be luckier. If it keeps enough cold gas, star formation may continue far longer than in a harsher environment. That is one reason some void galaxies still shine with the bluish light of younger stellar populations. They are not racing through life at the same pace as galaxies in crowded neighborhoods. Their fuel survives, and that survival changes everything. It lets them keep renewing themselves while other places in the universe have already settled into relative quiet. The result is almost poetic, though it is entirely physical. In the sparsest settings, the cosmos sometimes gives a galaxy more time, and it uses that time to keep lighting new suns. In some voids, galaxies line up like beads on dim filaments. A void is not always a smooth hollow with galaxies scattered at random. Sometimes a few of them appear in narrow alignments, almost as if someone threaded tiny points of light through the darkness. Those patterns hint at internal filaments so faint that they nearly vanish into the background. They are the ghostly remains of the same cosmic web that shapes the larger universe. Only here the structure is far more delicate. This matters because it shows that matter did not simply drain away from a void in a perfectly even way. Some routes retained slightly more gas and dark matter than others, and along those routes galaxies could still form or continue to gather material. To astronomers, such lineups are thrilling. They turn emptiness into a map. A handful of remote systems can reveal a hidden framework stretching across an underfilled region. Even where the universe seems nearly blank, it sometimes leaves behind the faintest geometry, traced only by a few patient lights. A void galaxy may spend ages falling toward almost invisible neighbors. Nothing in the universe is truly still. Even inside a vast, underfilled region, gravity continues its slow and patient work. A galaxy may look marooned in emptiness, yet over billions of years it can drift toward a faint group, a subtle filament, or a more massive structure waiting at the edge of the void. The motion is so gradual that it is almost impossible to feel on human terms. Light crosses the region faster than the galaxy changes its place within it. But the journey is real. This is one of the strange truths of cosmic emptiness. A void is not frozen. Matter continues to move through and around it, responding to gravitational pulls that may be far away and barely visible. So, a remote galaxy is not simply parked in darkness forever. It may be on a very long inward fall, tracing a path toward company so slowly that whole eras of stars can rise and fade before the voyage is complete. Gas from the cosmic web can still feed a lonely galaxy. A remote galaxy does not always survive by living only on its original supply. One of the most intriguing ideas in modern astronomy is that thin streams of gas can keep arriving from the surrounding cosmic web, even in relatively sparse environments. The flow may be weak and difficult to detect, but over vast stretches of time, it can matter enormously. Fresh gas can settle into the disk, replenish the fuel for future stars, and help explain why some isolated systems stay active far longer than expected. In certain cases, the incoming material may arrive from an awkward angle, bending outer gas layers or leaving strange motions that hint at a recent delivery. That changes the emotional picture completely. The galaxy is no longer a sealed island cut off from the universe. It is more like a remote harbor receiving rare shipments across unimaginable distances. The void may look empty, yet the hidden architecture of the cosmos can still send life-sustaining material inward. Some void galaxies are so faint they nearly vanish into darkness. Brightness is not the same as importance. A galaxy may be scientifically priceless and still appear as little more than a whisper in the data. Some remote systems are low in mass, diffuse in structure, or simply spread their stars so thinly that they barely stand out against the black. That makes them difficult to detect, which means the emptiest parts of the universe may be less empty than they first appear. Older surveys likely missed some of these faint inhabitants because the instruments were not sensitive enough to pick them out clearly. Each new generation of telescopes deepens the mystery by finding more subtle systems lingering at the edge of visibility. There is something thrilling about that. The universe is not only hiding galaxies in crowded places, it is hiding them in the lonely places too, where they almost dissolve into the background. A barely seen galaxy in a void can feel like the last visible ember in a region built mostly from absence. Others glow with fresh stars against a nearly empty background. Some remote galaxies do the exact opposite. Instead of fading into invisibility, they announce themselves with bright star-forming regions and the blue light of youthful suns. Against the sparse setting of a cosmic void, that can be striking. The wider neighborhood looks underfilled and subdued, yet the galaxy itself may be vivid, energetic, and still busy building new stellar populations. That contrast is part of what makes these systems so memorable. They feel like acts of defiance written in starlight. The emptiness around them did not prevent local clouds from collapsing, igniting, and filling the galaxy with fresh brilliance. In some cases, their isolation may even have helped by allowing them to keep their gas for longer. So what appears at first to be a lonely object in a quiet region turns out to be a place of ongoing creation. Even where the large-scale universe thins almost to nothing, the local story can still blaze with renewal. Their chemical makeup can preserve traces of a slower cosmic history. Every generation of stars changes a galaxy's chemistry. The first stars begin mostly with hydrogen and helium. Later generations inherit gas enriched by earlier stellar lives and deaths, carrying heavier elements forged in hot cores and violent explosions. Over time, a galaxy builds a chemical memory of its own past. In many remote systems, that record appears to develop more slowly. Their stars and gas can show lower abundances of heavier elements than similar galaxies in denser environments, hinting that enrichment unfolded at a gentler pace. That is a powerful clue. It suggests fewer intense episodes of rapid growth, fewer mergers stirring everything together, and a more patient build-up across cosmic time. For astronomers, this makes chemistry a form of biography. It is not just what the galaxy is made of. It is the long accumulated evidence of how quickly it has lived. In the emptiest regions, even the elements can whisper that the story unfolded with unusual slowness. Void galaxies often have fewer heavy elements than crowded galaxies. Astronomers use the phrase heavy elements for everything forged beyond hydrogen and helium, the raw materials the early universe made first. Those heavier ingredients build up slowly as stars live, die, and return enriched gas to space. In many remote galaxies, that enrichment seems less advanced. Their gas can remain more chemically simple than the gas in similar systems living in denser neighborhoods. That matters because chemistry is a record of how intensely a galaxy has been forming stars and recycling their remains. A lower abundance of heavy elements suggests a life with fewer dramatic bursts and a more patient pace of growth. In a crowded region, repeated interactions can stir gas, trigger star formation, and accelerate that chemical evolution. In a void, the process often takes longer. So when astronomers measure the composition of one of these lonely systems, they are not just reading numbers. They are hearing the echo of a slower, leaner, and more isolated history written into the atoms themselves. That makes them useful windows into simpler phases of galaxy building. Most galaxies we observe today have already lived through a great deal. They have merged, been disturbed, recycled gas many times, and layered one episode of history over another until the original picture becomes hard to untangle. A quieter system can be easier to read. When a remote galaxy keeps a lower mass, a cleaner structure, and a less enriched supply of gas, it can resemble an earlier stage in the long story of how galaxies assemble themselves. Not identical because nothing in the modern universe is truly ancient in that sense, but closer to the simpler conditions astronomers want to understand. These systems act like partial time machines. They do not send us backward, but they preserve features that crowded environments often overwrite. That is why they matter so much. They help researchers study how stars ignite, how disks settle, and how gas turns into structure when fewer outside complications are piling on. Sometimes simplicity is not primitive. Sometimes it is rare evidence left intact. Some are shaped like fragile spirals floating in deep solitude. There is something almost unreal about a spiral galaxy in a void. The shape feels too graceful for the setting, as if delicate arms of stars and gas should not be able to survive in such an immense region of scarcity. Yet some do. They turn slowly with their spiral pattern still visible, tracing arcs of light through a neighborhood where nearby galaxies may be astonishingly rare. The contrast is part of the magic. A spiral already looks like a structure drawn by patience, with stars orbiting in ordered paths and clouds of gas marking out regions where new suns can still appear. Place that design inside a giant cosmic hollow, and it becomes even more striking. These galaxies can seem like suspended pinwheels, preserved by the lack of frequent close encounters that might have torn or thickened their disks. They remind us that beauty in the universe does not require a crowd. Sometimes a fragile-looking form survives best in the loneliest possible setting. Others are irregular, messy, and full of unexpected star formation. Not every remote galaxy is a serene spiral. Some look unruly, almost improvised, as if the stars and gas never agreed on a final plan. Their shapes can be lopsided, clumpy, and hard to classify, with bright pockets of star formation appearing in places that seem oddly scattered. That apparent disorder is fascinating because it shows that emptiness does not produce only calm elegance. A sparse environment can still host turbulence, patchy gas collapse, and localized bursts of stellar birth. In smaller systems especially, gravity does not always sculpt a neat disk. Gas can be moved around by stellar winds, supernova explosions, or small-scale accretion, leaving the galaxy looking rough-edged and alive. These messy shapes are important clues. They suggest that internal physics can create drama even when outside disturbances are less common. A void does not force a galaxy into one tidy form. Sometimes it leaves the system free to develop a stranger and more chaotic personality of its own. A lonely galaxy can still host brilliant starburst regions. A starburst is what happens when star formation stops being modest and suddenly becomes intense. In one part of a galaxy, cold gas collapses quickly enough to produce a bright concentration of newborn stars, many of them massive, hot, and short-lived. The result can flood the surrounding region with blue light, fierce radiation, and the raw energy of stellar youth. What makes this so surprising in a void is the contrast of scales. The galaxy may live in one of the sparsest large-scale environments in the universe, yet inside it, a compact region can flare with extraordinary activity. That burst might be triggered by internal instabilities, by gas funneling inward, or by a minor interaction long after the galaxy seemed safely remote. However it begins, it proves an important point. Isolation on the cosmic map does not prevent local intensity. Even a galaxy with few neighbors can create a pocket of almost extravagant brilliance, as though the emptiness outside only sharpens the light within. Void galaxies challenge the idea that galaxies need busy neighborhoods. It is easy to assume that complexity comes from crowding. After all, galaxies in groups and clusters collide, trade gas, distort one another, and produce some of the most dramatic events in astronomy. That can make it seem as though a rich neighborhood is necessary for a galaxy to become interesting or fully developed. Remote systems prove otherwise. They show that a galaxy can grow a disk, form generations of stars, sustain internal structure, and carry out a long evolution without spending its life in cosmic traffic. That realization changes the way we think about galactic destiny. A crowd can accelerate change, but it is not the only author of change. Gravity, gas dynamics, stellar feedback, and long timescales can build remarkable systems even in relative solitude. In that sense, void galaxies are philosophical as well as scientific objects. They remind us that the universe does not need constant external commotion to make something rich, organized, and astonishingly alive with process. They show that emptiness can still nurture complexity and change. A void sounds like the opposite of productivity. The name suggests stillness, simplicity, and a shortage of possibilities. Yet the galaxies that inhabit these regions tell a different story. Even where matter is sparse on the largest scales, local systems can remain chemically evolving, dynamically structured, and full of ongoing transformation. Gas cools and collapses. Stars ignite and die. Radiation heats nearby clouds. Gravity reorganizes entire disks over immense timescales. In other words, the emptiness does not cancel complexity. It merely changes the setting in which complexity unfolds. That is a profound lesson, because it reveals how little the universe depends on crowding to create rich outcomes. A single galaxy in a great hollow can still contain millions of interlocking processes, all shaping one another in ways both subtle and dramatic. So, a void is not just an absence on the cosmic map. It is also a stage where intricate change continues, proving that even scarcity can be fertile. Even in a void, gravity keeps writing long, patient stories. Gravity is the great refuser of stillness. It works whether a region is crowded or sparse, whether the matter is arranged in blazing clusters or scattered thinly through a cosmic hollow. In the void, its work becomes slower and harder to notice, but it never stops. It guides the motions of galaxies, shapes the inflow of gas, and determines which small concentrations of matter survive long enough to become luminous systems at all. This is what makes void galaxies so mesmerizing. Their existence is evidence of gravity acting with unusual restraint, yet unbroken persistence. Nothing happened quickly there. The structures grew over long spans, sometimes with fewer collisions, fewer disruptions, and fewer dramatic shortcuts. The result is a story written in slow motion. A remote galaxy becomes the outcome of countless tiny pulls added together across billions of years. That kind of patience is difficult for the human mind to grasp. Yet it is one of the deepest truths of the universe, and voids display it beautifully. Astronomers hunt these galaxies to map the universe's hidden architecture. On the largest scales, the universe is not arranged like scattered marbles. It has shape. Matter forms filaments, walls, knots, and huge underdense regions between them. To understand that architecture, astronomers need tracers, visible markers that reveal where structure exists and where it thins out. Remote galaxies are some of the most important of those markers. By finding them and measuring their positions, scientists can outline the skeleton of the cosmic web and the hollows opening between its brighter strands. This is why even a faint galaxy deep inside a void matters. It helps define a region that otherwise might look like a blank patch on a map. The discovery of one more isolated system can sharpen the shape of a void, reveal an internal filament, or change how researchers model the flow of matter across cosmic time. In that sense, astronomers are not only collecting galaxies, they are using scattered lights to sketch the hidden design of the universe itself. Each one helps outline the borders of enormous cosmic emptiness. A void does not come with a bright edge. There is no luminous wall announcing where the emptiness begins or ends. Its boundaries have to be inferred by seeing where galaxies thin out, where filaments fade, and where the density of matter drops below the cosmic average. That makes individual galaxies extremely valuable. One remote system near the edge of a void can help define where the structure is still holding together and where the true hollow opens beyond it. It is a bit like mapping the shoreline of a dark sea by spotting only a few lonely lighthouses. Each light gives the larger shape more precision. This is one reason astronomers care so much about positions as well as properties. A galaxy is not just interesting because of what it contains. It is also important because of where it sits. Its location helps transform an abstract emptiness into a measurable structure with extent, contour, and a place in the grand geography of the cosmos. Without void galaxies, many voids would be much harder to trace. The emptiest parts of the universe are difficult to map precisely because emptiness does not shine. Astronomers cannot simply photograph a void the way they photograph a star cluster. Instead, they infer its presence from what surrounds it and from the few galaxies that still inhabit it. Those rare occupants are crucial. They provide anchor points in regions where visible landmarks are scarce. Remove them, and many voids would become much harder to define with confidence. Their internal structure would blur, their shapes would be less certain, and the transition between hollow and filament would be more difficult to pin down. That makes every isolated galaxy unusually important. It is not just surviving in a sparse region. It is helping reveal the existence of that region in the first place. A void might seem like the triumph of absence, yet its identity often depends on a handful of survivors. The emptiness becomes legible because a few faint galaxies continue to shine within it. Their positions reveal where matter gathered and where it failed. A map of galaxies is also a map of success and failure on the largest scale. Where galaxies crowd together, matter gathered efficiently enough for gravity to build dense structures. Where they become rare, the process was weaker, slower, or redirected elsewhere. The positions of remote galaxies are therefore more than coordinates. They are records of how the early universe developed unevenly, with tiny differences in density growing into the vast contrasts we see today. A galaxy inside or near a void marks a place where some structure did manage to form, though much less than average. Its absence from another nearby region may show where matter drained away too effectively for a similar system to arise. This makes spatial arrangement deeply meaningful. Astronomers can read it almost like topography, with ridges of abundance and basins of scarcity. A lonely galaxy is part of that story. It is one visible sign of where gravity barely won, in a region where it often came close to losing. Voids grew as matter drained away into walls, clusters, and filaments. The emptiest regions of the universe were not carved out with a cosmic scoop. They emerged because gravity amplified small differences present in the early universe. Regions that began slightly denser pulled in more matter over time, becoming the rich filaments, walls, and clusters that now shape the cosmic web. As that happened, neighboring underdense regions lost material and became emptier still. In other words, voids grew because matter was being siphoned away from them into the structures around the edges. That process is one of the most beautiful ideas in cosmology. The great hollows we see today are not static gaps. They are the result of motion, of matter flowing outward from the poorest regions and piling up elsewhere. A void galaxy therefore lives in a place shaped by loss. Its surroundings became sparse because the universe was redistributing its resources on an unimaginable scale. The galaxy remains as one of the few lights left behind, while the larger evacuation continued around it. That left certain galaxies marooned in expanding seas of darkness. As voids grew emptier, the few galaxies already living inside them became more and more isolated. The structures around the edges kept gaining matter, while the hollows widened and deepened, increasing the sense of separation. A galaxy in such a region could end up marooned, not in the romantic sense of a stranded ship, but in the precise cosmological sense of being left behind in a place that surrounding matter was gradually abandoning. That image matters because it captures the dynamic history of these regions. The isolation was not always as extreme as it appears today. It intensified over time as the void expanded and the denser edges became more pronounced. So a lonely galaxy can be thought of as a survivor of a changing landscape. It formed when conditions still allowed it, then watched the larger environment become steadily more deserted. By the present era, it may inhabit a true sea of scarcity, shining where the rest of the cosmic population has drifted farther and farther away. Some void galaxies may have formed from unusually gentle beginnings. A galaxy's first steps matter. In dense regions, the early environment can be turbulent, full of nearby structures competing for gas and shaping growth through repeated gravitational nudges. In a void, the opening chapter may have been calmer. The initial concentration of matter was weaker, the surrounding competition lower, and the pace of assembly more restrained. That gentler beginning may help explain why some remote systems remain smaller, less chemically enriched, and less heavily disturbed than their cousins elsewhere. Their foundations were laid in a quieter setting, and that early calm may echo through the rest of their lives. This does not mean their stories lacked drama altogether. Star formation, internal feedback, and occasional encounters still matter enormously. But the starting conditions were different, and starting conditions can leave long shadows. To study one of these galaxies is to ask how much of its later character was already implied by the stillness of its birth. Sometimes destiny begins with the way the universe first gathered around you. Their quiet lives can expose which galactic traits come from nature. One of the hardest problems in astronomy is separating what a galaxy is born inclined to become from what its neighborhood later forces upon it. A dense environment can scramble that distinction because external influences pile up so quickly. Gas is stripped, orbits are perturbed, and mergers rewrite the shape of the system. A quieter galaxy offers a cleaner test. If a remote system develops a bar, a bulge, a spiral pattern, or a particular style of star formation with relatively little outside disturbance, that feature is more likely to reflect internal processes rather than environmental damage. This is why isolated galaxies are so useful. They help astronomers identify the traits that arise from a galaxy's own gravity, angular momentum, gas supply, and stellar feedback. In other words, they show what galactic nature looks like before too much nurture interferes. That does not solve every mystery, but it brings the question into sharper focus. A solitary system can reveal what a galaxy does when left more largely to itself. The surroundings also show which traits come from cosmic neighbors. The comparison only becomes powerful when you place remote galaxies beside similar systems in busier environments. Then the differences begin to speak. If one class keeps more gas in sparse regions but loses it in clusters, environment is implicated. If one shape survives in a void but is commonly distorted in dense groups, neighbors are likely part of the cause. This is how astronomers use isolation as a control. A galaxy alone is interesting, but a galaxy alone compared with a galaxy in a crowd becomes a test of what outside influence can do. Some traits may turn out to be remarkably robust, appearing almost regardless of surroundings. Others may depend strongly on whether the galaxy spent its life being jostled, stripped, or merged. The setting becomes an explanation. In that sense, a void does not just reveal solitude. It reveals contrast. By studying what remote systems keep and what crowded systems lose, scientists can see the fingerprints of neighbors all across the architecture of galactic evolution. In crowded regions, galaxy evolution can be loud, fast, and violent. A dense cluster is one of the universe's busiest neighborhoods. Galaxies race through hot gas, tug at one another, lose material to their surroundings, and sometimes collide or merge outright. The result can be dramatic. Star formation may flare and then shut down. Disks can be thickened or transformed. Gas can be stripped away in long, trailing plumes. Central black holes may be fed by disturbances that drive material inward. Everything happens under pressure. These crowded regions are thrilling to study because the pace of change can be so intense, but they also complicate the story. When many forces act at once, it becomes harder to tell which one produced which result. That is why the contrast with void galaxies is so useful. A crowded system shows what happens when the environment is constantly intervening. The galaxy does not simply evolve. It gets handled, buffeted, and sometimes radically rewritten by its surroundings, like a life lived in the middle of perpetual cosmic weather. In voids, the universe sometimes whispers instead of shouts. That difference in tone is one of the most beautiful things about these galaxies. In a busy cluster, evolution can be dramatic and abrupt, with clear signs of stripping, collisions, and crowd-driven upheaval. In a void, the changes are often quieter. Gas settles more gradually. Rotation can remain more orderly. Star formation may continue at a steadier pace. The shaping forces are still there, but they often work with less interruption and over longer spans of time. That is what it means for the universe to whisper. It does not stop acting. It simply acts more patiently. This softer mode of evolution is scientifically precious because it reveals processes that can be drowned out elsewhere. You begin to notice the slow consequences of internal gravity, of careful gas inflow, of minor asymmetries growing over ages. A remote galaxy, therefore, becomes an instrument for hearing the lower volume notes in cosmic history, the ones that louder environments often overwhelm before we can fully listen. That whisper can still build stars, disks, and central bulges. A quieter environment does not mean a galaxy stays unfinished. Even without constant disturbances from neighbors, the ordinary machinery of galaxy building keeps working. Gas settles into rotating structures and helps form disks. Clouds collapse into stars, generation after generation. Over long spans of time, material can drift inward and contribute to a denser central concentration, helping create a bulge at the heart of the system. None of this requires a crowded neighborhood. It requires gravity, time, and enough raw material to keep the process going. That is why void galaxies are so revealing. They show that much of galactic architecture can arise through persistent internal evolution, rather than through repeated outside shocks. The structures may grow more slowly and the details may differ, but the result can still be rich and recognizable. A galaxy does not need the universe to shout instructions at it. Sometimes a long whisper is enough to build a luminous disk, a thriving stellar population, and a central heart of stars. Some void galaxies keep surprisingly large reservoirs of cold hydrogen. Cold hydrogen is one of the great hidden treasures of a galaxy. You cannot usually see it glowing the way stars do, yet it is the raw material from which future stars can eventually form. In many remote systems, astronomers have found that this supply can remain impressively abundant. That is surprising because these galaxies often look modest in size, and they live in regions where the wider environment seems almost stripped of opportunity. But the fuel is there, spread through disks and outer regions, like a silent promise of future light. In busier neighborhoods, gas can be heated, stirred, or pulled away more easily. In the void, some galaxies appear to hold on to it for longer. That changes how their stories unfold. A galaxy with a deep reserve of cold hydrogen is not living only on its past. It is carrying the possibility of new stars within it, waiting for gravity to begin the next chapter. That fuel can sustain star formation for very long times. A galaxy does not make stars all at once and finish the job. It depends on a continuing supply of gas, especially the colder material that can collapse into dense clouds and ignite new suns. When that supply lasts, the galaxy can keep renewing itself across extraordinary stretches of time. That is one reason some void galaxies remain so captivating. They may not blaze with the frantic intensity of a giant merger, yet they can continue forming stars long after harsher environments have already drained similar systems of opportunity. The process is slow, but that slowness is part of the fascination. A modest galaxy, isolated inside a huge, underfilled region, may still be turning gas into starlight, while the universe ages around it. In human terms, the timescale is beyond comprehension. Entire civilizations could rise and vanish without changing the picture at all. The galaxy would still be there, patiently converting a hidden reserve into generations of new suns. Radio telescopes are especially good at finding their hidden gas. If you relied only on ordinary visible light, you would miss part of the story. Stars reveal where a galaxy has already spent its fuel, but radio observations can uncover what still remains. Cold hydrogen gives off a very specific signal at radio wavelengths, and telescopes tuned to that signal can detect vast reservoirs of gas that optical surveys cannot show so clearly. This is one reason radio astronomy is so important for void galaxies. A system that looks small or unremarkable in visible light can suddenly become much more interesting when its gas supply is revealed. The galaxy stops looking like a fading ember and starts looking like a place with future potential. That hidden dimension changes the emotional picture as well as the scientific one. We are not only seeing what the galaxy is, we are seeing what it may still become. In the loneliest parts of space, radio telescopes act almost like secret listeners, picking up the quiet resources that keep these systems alive. Optical surveys reveal how lonely their visible neighborhoods really are. To understand how isolated a galaxy truly is, astronomers need more than a close-up portrait. They need a map of everything around it. Optical sky surveys provide that wider view by collecting the light of huge numbers of galaxies across vast stretches of space. When researchers place a suspected void galaxy into that broader context, the results can be astonishing. The surrounding region may contain far fewer luminous companions than expected, with long distances separating one substantial system from the next. That emptiness becomes visible not because the void itself shines, but because the normal crowd of galaxies is missing. This is how loneliness becomes measurable. A galaxy that might seem ordinary on its own turns out to inhabit a remarkably sparse address when set against the larger pattern. The beauty of optical surveys is that they make absence legible. They show where the bright strands of the cosmic web are, and just as importantly, where those strands give way to immense hollows. Computer simulations predict void galaxies should be common, but elusive. When cosmologists model the growth of structure in the universe, they do not get a cosmos made only of bright clusters and dense filaments. They also get enormous underfilled regions, and within those hollows, the models often predict many small galaxies living difficult-to-detect lives. In that sense, void galaxies are expected. The puzzle is that finding all of them in reality is much harder than building them in a simulation. Many are likely faint, diffuse, or too low in mass to stand out easily in older surveys. So theory says there should be a substantial hidden population, while observation has had to work much harder to catch up. That tension is fascinating, because it shows the boundary between what the universe may contain and what our instruments can currently reveal. It also means every new detection matters. Each remote galaxy discovered in a void is not only an object in the sky. It is a test of whether our cosmic models are truly seeing the same universe we are. Many are dim enough to slip past older galaxy surveys. The universe does not hide all its secrets behind distance alone. Sometimes it hides them in faintness. A galaxy can be nearby on cosmic scales and still remain difficult to detect if its stars are spread thinly, if its surface brightness is low, or if it simply never built a large luminous population in the first place. This is especially important in voids, where astronomers expect many smaller systems that do not announce themselves boldly. Older surveys, however impressive they were for their time, often had limits. They could miss diffuse galaxies that blended into the background or failed to reach the brightness thresholds needed for confident detection. That means some of the apparent emptiness may have been partly a problem of visibility. The void looked cleaner because the faintest residents were being overlooked. As techniques improve, the picture becomes richer and stranger. The lonely regions do not stop being lonely, but they begin to reveal more of the subtle population that was there all along. Better telescopes keep uncovering lonelier systems than expected. One of the most exciting patterns in modern astronomy is that improved instruments do not merely confirm what we already knew. They often deepen the mystery. As telescopes become more sensitive and surveys push farther into faint territory, astronomers continue finding galaxies that are even more isolated than earlier maps suggested. Some are dimmer. Some sit deeper inside voids. Some occupy neighborhoods so sparse that their existence feels almost improbable. This matters because it tells us the universe still has levels of solitude we had not fully appreciated. The better we get at seeing, the more extreme the emptiness can appear. That is a thrilling reversal. You might expect deeper observation to simply fill the map and reduce the strangeness. Instead, it often sharpens the contrast, revealing both more hidden galaxies and more severe isolation. Each newly found system becomes a reminder that the large-scale universe is still not fully charted. Even now, better eyes keep discovering lonelier lights in darker places. Each discovery refines our picture of the cosmic web. The cosmic web is one of the grandest patterns in nature, yet no one can see it all at once with the naked eye. It has to be reconstructed from the positions of galaxies, the distribution of gas, and the behavior of matter across enormous distances. That means every new void galaxy matters more than its size might suggest. Its location can sharpen the outline of a filament, hint at an internal strand, or confirm that a region truly is as empty as it appears. A single data point in the right place can change the geometry of a much larger map. This is what makes the search so exciting. Astronomers are not only cataloging isolated objects, they are steadily improving humanity's portrait of the universe's hidden framework. The web becomes clearer not through one dramatic revelation, but through many careful additions. Each remote galaxy adds one more stitch to the pattern, helping us see how crowded structures and vast hollows fit together in the larger design. A void galaxy may have only a few nearby companions. Isolation in astronomy is rarely absolute. Even a galaxy deep in a sparse region may have a handful of smaller neighbors orbiting nearby or lingering at modest distances. That detail makes the situation more interesting, not less. Instead of a single light in perfect solitude, you get a tiny local society adrift inside a much larger emptiness. The central galaxy may still dominate the scene, but a few companions can add complexity to its life. They can supply gas, stir the outer disk, or serve as clues to how matter managed to gather in such a thin environment at all. There is something striking about that contrast. On the scale of the immediate neighborhood, there may be a few familiar relationships playing out. On the scale of the wider cosmos, the whole group is still astonishingly alone. So the galaxy is not necessarily isolated in every sense. It is isolated against the backdrop that matters most, the huge, underfilled landscape surrounding its small circle of company. Those few companions can still tug hard over immense timescales. A minor companion does not need to be massive to matter. Gravity is patient, and patience changes everything. A small satellite galaxy orbiting a larger remote system can gradually distort the outer gas, stir stars into asymmetry, or trigger slow structural changes that become dramatic only after vast spans have passed. Time. The interaction may be weak in any single moment, but over hundreds of millions or billions of years, it can leave clear marks. This is one of the reasons void galaxies remain so compelling. Even in regions with very few neighbors, relationships still matter. A companion that seems insignificant on first glance may end up reshaping the host more effectively than anyone would expect, precisely because the process has so much time to work. There is no need for a violent crowd scene. A single persistent gravitational partner can be enough. In the quietest parts of the universe, even a small tug can become a major chapter if the cosmos is willing to wait long enough. Some void galaxies sit near the very centers of vast emptiness. These are the true deep dwellers, the systems that do not merely brush against underdense space, but occupy the innermost parts of enormous cosmic hollows. Their position makes them especially fascinating because they are farthest from the richer structures at the edges. They live where the scarcity is most severe, where visible neighbors can be astonishingly distant, and the surrounding matter is thinnest on average. A galaxy in such a setting feels almost improbable, as though gravity managed to strike a small success in one of the least favorable regions available. For astronomers, these systems are precious because they offer the clearest example of life inside the heart of a void. They are not transitional objects hovering near busier territory. They are residents of the deepest underfilled zones. To study one is to come as close as we can to asking what galaxy evolution looks like in the most isolated large-scale environment the universe naturally provides. That makes them unforgettable scientific targets. Others live closer to the edges where filaments begin. The boundary of a void is often more active than its center. This is where the great hollows start giving way to filaments, walls, and other richer structures of the cosmic web. Galaxies living near those edges occupy a special position. They are still part of the sparse environment, yet they lie closer to the regions where matter is gathering more strongly. That means their lives can be more complicated than those of the deep dwellers. They may receive more gas, encounter more subtle gravitational influences, or sit on the threshold between two very different cosmic moods. In a sense, they are borderland galaxies, standing where emptiness begins to surrender to structure. That makes them excellent comparison cases. By studying systems near the edges and systems near the centers, astronomers can ask how much even a modest change in location affects growth, chemistry, and star formation. A void is not the same everywhere, and the edge can be a very different world from the middle. Their location inside a void can shape how they evolve. Not all isolation is equal. A galaxy near the center of a void may experience a very different long-term history from one living closer to the rim. Position determines how much gas might still trickle in, how likely minor companions are to appear, and how strongly the surrounding large-scale structure continues to influence motion. This is why astronomers care not only that a galaxy is in a void, but where in the void it resides. The answer can help explain differences in color, gas supply, structure, and pace of growth. A central system may live a more extreme form of solitude. An edge system may remain connected to faint filaments or nearby substructure. In both cases, the environment matters, but it matters in subtly different ways. This turns the void into something more than a single category. It becomes a landscape with gradients. A galaxy's address inside that landscape can change the tempo of its life, even when the broader setting is still one of profound emptiness. EJ galaxies may receive more gas and more occasional interactions. A galaxy near the rim of a void is closer to the denser architecture beyond it, and that proximity can make a real difference. Thin streams of gas may be easier to access there, and faint neighboring systems may be more numerous than they would be deep in the center. The result is a life that can still feel sparse by cosmic standards, yet with more opportunities for subtle change. An edge galaxy might gain fuel more readily, hold on to a slightly busier local environment, or experience the kind of minor interaction that nudges star formation into a new phase. None of this turns the rim into a crowded neighborhood. It simply means the border can be more connected than the core. That contrast is scientifically useful because it lets astronomers explore a range of conditions within the same general void environment. The closer a galaxy lies to the web beyond the hollow, the more chances it has to feel the universe reaching back in. Central void galaxies can be the real hermits of cosmology. Among all the lonely systems astronomers study, these may be the most extreme. A galaxy near the center of a large void can be separated from rich surrounding structure by astonishing distances, with few substantial neighbors and only the thinnest trace of the cosmic web reaching inward. The word hermit fits because the isolation is not casual. It is structural, deep, and persistent across immense spans of time. Such a system becomes a rare kind of cosmic experiment. It lives with less interference, less easy access to fresh material, and a more severe version of emptiness than galaxies at the edges. This does not make it dead or featureless. On the contrary, that is what makes it so compelling. Whatever stars it forms, whatever structure it builds, whatever chemical history it records, all of it unfolded under some of the sparsest large-scale conditions available. These galaxies are not just isolated. They are among the clearest embodiments of cosmic solitude ever found. Those helmets help test theories about dark matter and structure formation. The deepest void galaxies are useful precisely because they are so demanding. Any successful theory of structure formation has to explain how galaxies arise not only in rich clusters and bright filaments, but also in the least favorable large-scale environments. A central void galaxy is therefore a challenge thrown at cosmology. It asks whether our models of dark matter halos, gas accretion, and long-term growth can reproduce such a remote survivor without cheating the conditions. If the predicted population is too large, too small, too bright, or too faint compared with what we observe, the theory needs attention. This makes the loneliest galaxies some of the most revealing ones. They push models into the regime where the scaffolding is weakest and the margins are smallest. In that sense, the deep dwellers are not peripheral to cosmology. They are central tests of it. A galaxy thriving in a great hollow can expose whether our account of how the universe builds structure is truly complete. Some researchers compare voids to laboratories with fewer confusing variables. Astronomy cannot run controlled experiments in the ordinary sense. Galaxies are too large, too distant, and too ancient to place in test chambers. Yet nature sometimes offers approximate experiments of its own. A void can serve as one of those because many of the complicating influences common in denser environments are reduced there. Fewer close encounters, less stripping by hot cluster gas, and a lower frequency of major mergers mean that some questions become easier to ask. If a remote galaxy still forms a bar, still preserves a thin disk, or still builds stars in a particular pattern, the explanation may lie more in internal physics than in environmental disruption. That is why the laboratory comparison is so appealing. It does not mean voids are simple. They are not. It means they can be clearer. By reducing some of the noise, they allow astronomers to isolate important processes with greater confidence. The emptiest places can become the cleanest places to think. Void galaxies let astronomers study environment with unusual clarity. Environment influences almost everything in galaxy evolution, yet in busy regions, its effects can overlap so heavily that interpretation becomes difficult. A cluster can strip gas, trigger encounters, alter orbits, and feed central activity all at once. In a void, the picture can become more legible. With fewer outside forces acting simultaneously, astronomers can watch how isolation itself changes the life of a galaxy. Does the gas last longer? Does the structure remain more ordered? Does chemical enrichment proceed at a different pace? These are not abstract questions. Remote systems let researchers test them against real objects. The clarity comes from contrast. A galaxy in a sparse hollow and a similar galaxy in a crowded group may share mass and basic ingredients, yet diverge because their surroundings impose different pressures. That makes void galaxies scientifically elegant. They reveal the role of environment not by eliminating it, but by presenting it in a quieter and more stripped-back form, where its effects can be read more distinctly. They also reveal how emptiness itself changes over cosmic time. A void is not a static hole preserved from the early universe. It grows, deepens, and changes shape as matter continues to migrate toward denser structures elsewhere. That means void galaxies are more than isolated systems. They are witnesses to the evolution of emptiness itself. Their positions, motions, and histories help astronomers understand how underdense regions develop across billions of years. A galaxy near the center today may not have felt quite so isolated in the distant past. A galaxy near the edge may eventually find the boundary moving in relation to it as surrounding structures sharpen. This makes the study of voids strangely dynamic. We are not looking at permanent cosmic deserts, but at regions whose scarcity has been intensifying over time. The galaxies living there preserve part of that story. Their very isolation is evidence that the universe has continued to rearrange matter on the largest scales, making some places richer and other places emptier as the ages unfold. A growing void can push galaxies apart as structures sharpen. The effect is subtle, but profound. As denser regions draw in more matter, the neighboring underdense regions effectively lose it, and the contrast between rich and poor areas becomes stronger. In that process, galaxies inside or near a void can end up farther apart over time, not because they are repelling one another in the ordinary sense, but because the surrounding large-scale structure is evolving in a way that widens the hollow. The emptiness becomes more pronounced as walls and filaments sharpen around it. This gives voids an almost expanding character within the larger cosmic flow. Galaxies that once lived in a merely sparse region can find themselves in a much deeper one later on. The image is extraordinary. A few luminous systems drifting ever farther across a darkening basin, while the brighter architecture beyond the rim grows more defined. It is one more reminder that emptiness is not passive. Even nothing much can become more by becoming less. The emptiest places in space still expand with the rest. A void is not a frozen pocket sealed off from the larger universe. It shares in cosmic expansion just as everything else does. Space itself continues stretching, even across regions where matter is scarce and galaxies are few. That means a lonely system inside a vast hollow is not sitting in stillness. It is being carried along in the same expanding fabric that separates all distant structures over time. The difference is that in a void, there is less matter around to resist that widening through gravity. Rich clusters can hold themselves together locally. Filaments can keep their shape through shared mass. But the underdense regions feel the general expansion with unusual clarity. This is part of what makes them so revealing. They are not outside cosmic history. They are among the clearest places to watch its broadest motion at work. Even the loneliest galaxy is still riding the same growing universe as every cluster, wall, and spiral we know. That expansion helps make voids emptier as the universe ages. A void does not merely stay empty. In many cases, it becomes emptier. As the universe expands and gravity pulls matter into denser structures elsewhere, the contrast sharpens between crowded regions and underfilled ones. Filaments gain definition. Walls become clearer. Clusters deepen their hold. Meanwhile, the hollows between them lose relative density and can widen. The effect is almost like bubbles growing in rising bread, except the dough is the cosmic web itself. This makes emptiness a dynamic thing rather than a static backdrop. A galaxy living in such a region may find its surroundings becoming more sparse across billions of years, even if the galaxy itself continues to make stars or hold on to gas. That is one of the strangest ideas in cosmology. Nothing much can still evolve. A void is shaped not only by what formed there early on, but by the long history of matter leaving and structure elsewhere becoming stronger. Void galaxies are not outside the cosmic web, just stranded within it. It is tempting to imagine these systems as if they had somehow slipped beyond the universe's great network. They have not. They remain part of the same cosmic web as every cluster and filament. The difference is that they occupy its thinnest, weakest reaches, where the structure is stretched almost to breaking. A void galaxy is still connected by gravity, dark matter, and the faint legacy of how matter was distributed in the early universe. It has not escaped the web. It has simply ended up on one of its most tenuous strands, or in a hollow where the network barely left anything behind. That image matters because it turns isolation into context. These galaxies are not exceptions to the cosmic pattern. They are extreme expressions of it. They show what the web looks like when it runs low on material and still somehow manages to leave one luminous system shining inside the sparse remains of a much larger design. Even loneliness in space still follows the rules of gravity. Isolation may feel emotional to us, but in cosmology, it is mechanical. A galaxy in a void is still obeying the same laws as one in a rich cluster. Its stars orbit because gravity holds them. Its gas settles or stirs because gravity shapes the disk. Its dark matter halo still anchors the system in invisible mass. Even its loneliness is the product of gravity acting over immense time, drawing matter away into denser regions and leaving the underfilled parts behind. That is why void galaxies are so beautiful to think about. They are not rebels against the cosmic order. They are among the purest demonstrations of it. When matter is scarce, gravity does not stop. It simply works with fewer ingredients and over longer spans. The result can be a galaxy that feels almost impossibly alone, yet every part of its history, motion, and survival still comes down to the same universal force that builds clusters and bends light across the sky. Some void galaxies may spin faster than their modest sizes suggest. One of the delights of astronomy is that appearances can mislead. A galaxy that seems small, faint, or understated may still have surprisingly swift rotation once astronomers measure how its gas and stars move. In remote systems, that can feel especially striking. A modest disk in a sparse region might turn with more speed than its visible structure alone would lead you to expect. That matters because rotation is a clue to the mass hidden inside, especially the dark matter halo that does much of the holding together. A galaxy can look delicate and still be dynamically powerful. In a void, that contrast becomes even more interesting because the system formed and evolved in such a thin environment. If it spins rapidly despite its quiet address, then the invisible framework inside it must still be substantial enough to guide the motion. Sometimes the loneliest galaxies remind us that calm appearance and deep internal strength are not the same thing. Others seem too active for neighborhoods that quiet. This is one of the reasons void galaxies are so hard to forget. You expect emptiness to produce passivity, yet some remote systems look busy, blue, chemically evolving, and still full of ongoing star formation. They can appear too lively for the sparse, large-scale regions they inhabit. That mismatch is scientifically precious because it tells astronomers that a quiet neighborhood does not guarantee a sleepy internal life. Gas may still be arriving. Stored fuel may still be plentiful. Local instabilities may still be driving clouds to collapse and ignite new stars. A galaxy can inhabit one of the least crowded parts of the universe and still behave like a place where important things are happening right now. That tension between setting and behavior is part of what gives these objects their strange beauty. They seem to contradict the mood of their surroundings, as if the emptiness outside only makes their internal activity more vivid by contrast. These surprises make void galaxies scientifically precious and deeply strange. Astronomy loves the ordinary because patterns matter, but it also loves the exceptions that reveal where our understanding is incomplete. Void galaxies offer both at once. They fit into the broader picture of cosmic structure, yet they often behave in ways that feel unexpectedly vivid, resilient, or peculiar for their setting. Some hold more gas than expected. Some keep forming stars. Some preserve tidy disks. Others look warped or unusually active. Each surprise turns the emptiest environments into places of scientific leverage. If a theory can explain only crowded systems, it is incomplete. If it cannot account for galaxies thriving in such sparse conditions, it is missing part of the universe. That is why these remote systems matter far beyond their numbers. They probe the edges of our models, where the assumptions are most likely to fail. And they do it with style. A lonely galaxy in a giant void is not only an object of research, it is one of cosmology's most elegant challenges. A galaxy can be isolated yet still full of internal drama. Large-scale solitude and local turbulence are not opposites. A galaxy may live far from major neighbors and still contain all the restless machinery that makes galaxies fascinating. Gas clouds can collide and fragment. Massive stars can flood whole regions with radiation. Stellar winds can carve cavities through the interstellar medium. A central black hole may feed fitfully, and magnetic fields may help shape how matter moves through the disk. In other words, the wider emptiness does not impose calm on every smaller scale. That contrast is part of the subject's power. The same system that looks lonely on a map of the universe can, from the inside, be a place of motion, heat, feedback, and ongoing change. It is a reminder that scale alters meaning. A galaxy can be cosmologically remote and astrophysically busy at the same time. The hush belongs to the neighborhood. The drama belongs to what is happening inside the island of stars itself. Supernovae still explode there, lighting emptiness with brief violence. A void does not cancel the life cycles of stars. When massive stars are born in one of these remote galaxies, some of them will still die in catastrophic explosions. For a short time, a supernova can rival the light of enormous stellar populations around it, blasting radiation and shock waves through the surrounding gas. That is a thrilling thought. In one of the sparsest large-scale environments in the cosmos, a single dying star can briefly flood a lonely system with extraordinary brilliance. The wider void remains dark and underfilled, yet inside the galaxy there can be moments of fierce release, moments when heavy elements are hurled outward and nearby clouds are shaken into new possibilities. These explosions matter scientifically because they enrich the gas, stir the interstellar medium, and help regulate future star formation. They also matter emotionally because they show how even the quietest cosmic address can still host flashes of violence so bright they would redefine the night if you were there to see them. Star clusters still form there, despite the surrounding cosmic hush. A star cluster begins when a cloud of gas collapses into many stars at once, creating a family born from the same reservoir and roughly the same time. That process does not require a crowded universe. It requires local gas, gravity, and the right conditions inside the galaxy itself. So even in a void, where the wider environment may feel almost deserted, star clusters can still emerge as compact, brilliant gatherings of youth. That is one of the most charming truths about these galaxies. They do not only form isolated stars scattered quietly through a disk. They can create dense stellar communities, luminous knots where many suns are born together. A cluster in a void galaxy is a kind of defiance, a concentrated burst of companionship inside one of the most isolated settings imaginable. It reminds us that the emptiness belongs to the large-scale backdrop. Locally, the usual cosmic creativity continues, and gravity still knows how to gather matter into bright communal structures. Planetary systems could exist in galaxies with astonishingly dark skies. Where stars form, planets may follow. That simple possibility becomes wonderfully eerie in the context of a void galaxy. A world orbiting an ordinary star in such a system might still have familiar local sights, a sun, perhaps moons, maybe neighboring stars in the home galaxy. But the wider extragalactic sky could be profoundly different. With fewer nearby galaxies and a sparser cosmic neighborhood, the universe beyond the host galaxy might appear markedly lonelier. This does not mean planets are especially likely in voids, or especially unlikely. It means the conditions for planetary systems are not ruled out merely because the galaxy sits in a sparse, large-scale environment. If anything, the idea expands the imagination. There could be worlds where life, if it ever arose, would grow up under a sky shaped by unusual cosmic solitude. The home galaxy could still be bright and structured, while the rest of the universe looked more distant, darker, and strangely more silent than our own familiar extragalactic backdrop. Night inside a void galaxy might feel different on every scale. That is the haunting part of this subject. Locally, the sky could still be rich with stars, nebulae, and the glow of the home galaxy's own structure. On the scale of the host system, much might look familiar to any civilization living inside a spiral or irregular galaxy. But farther out, the difference would emerge. Beyond the local stars, the broader universe could seem markedly less crowded. Fewer bright neighboring galaxies might decorate the darkness. The nearest large companions could lie much farther away than they do for us. So the same night would carry two truths at once. Nearby, abundance. Far away, scarcity. That layered experience is what makes void galaxies so evocative. They are not places where everything disappears. They are places where the outer scales fall away first, leaving a local highland of light surrounded by a cosmos that may look more remote and less socially populated than the one we inhabit from our denser corner of the web. Neighbor galaxies would often appear fewer, fainter, and more distant. Our own view of the universe is shaped by living in a relatively populated region. The Milky Way has notable neighbors, satellite galaxies, and the great presence of Andromeda nearby. In a void galaxy, that kind of company may be much rarer. A civilization there, if one existed, might find that large neighboring galaxies are sparse on the sky and often much farther away. Many would appear faint because the distances are larger and the local density is lower. This changes the cosmic mood. The universe beyond the host galaxy would not vanish, but it could look less richly furnished than the one we infer from our own environment. That difference matters because observation begins with perspective. The same laws would still hold. The same cosmic expansion would still unfold. Yet the visible social life of galaxies would be quieter. A sparse neighborhood on the largest scales could translate into a night where the external universe feels more remote, more selective, and more difficult to map by eye alone. The broader universe might seem lonelier from such a world. Perspective shapes feeling, even in science. If intelligent observers ever arose inside one of these galaxies, their picture of the cosmos might begin from a different emotional baseline than ours. They could still discover stars, physics, planetary motions, and the grandeur of their own host galaxy. But beyond that immediate setting, the visible universe might offer fewer nearby systems to suggest rich galactic society. The nearest major companions could be more distant. The larger cosmic pattern might be harder to infer at first glance. In that sense, the broader universe could appear lonelier, not because the cosmos contains less overall, but because the observer's own region supplies fewer obvious external lights. That possibility is deeply evocative. It reminds us that cosmology is partly conditioned by where one stands. A species born in a void galaxy might need more patience and more powerful instruments to discover what we learned from a somewhat busier address in the great web of matter. Yet the local stars inside that galaxy could still blaze brilliantly. This is the balance that keeps void galaxies from feeling empty in a simple way. The large-scale environment may be sparse, but the galaxy itself can still contain billions of stars. Some may be ancient and red. Some may be young and blue. Some may gather in clusters or light up star-forming regions with fierce intensity. So a world inside such a galaxy would not necessarily live under a poor sky. On local scales, it could still have a magnificent stellar backdrop, with dust lanes, nebulae, and the broad luminous sweep of the home system itself. The loneliness only truly reveals itself when you look beyond that. This makes void galaxies especially poetic scientific objects. They combine inner richness with outer scarcity. They are reminders that emptiness and brilliance can coexist at different scales without contradiction. A galaxy may be one of the loneliest islands in the cosmic ocean, and still, from within, look full of light, structure, and immediate astronomical beauty. Void galaxies remind us that emptiness is never truly empty. A cosmic void sounds like the end of content, but physics refuses such simplicity. Even where galaxies are scarce, there is still dark matter shaping gravity, thin gas drifting between structures, background radiation crossing all of space, and the wider expansion of the universe itself. A void is empty only by comparison. Against the crowded richness of clusters and filaments, it looks sparse, yet it is still part of a living cosmos threaded by forces and faint material. This is why void galaxies matter so much. They stand in places that teach us the difference between everyday language and cosmological reality. Empty does not mean nothing. It means much less than average, but still enough for gravity to work, for light to travel, and for a galaxy to survive. In that sense, the loneliest systems are also clarifying ones. They expose the hidden content of the universe by making the visible content so rare that the unseen parts become impossible to ignore. Dark matter, thin gas, and ancient light still cross the void. The large hollow around a void galaxy may look like a blank gulf, but it is not sealed off from the rest of existence. Dark matter still extends through it, though at lower density than in the richer regions beyond. Very diffuse gas still occupies the space between galaxies. And radiation, including ancient photons that have traveled since the early universe, continues crossing those regions freely. This means a void is less like an abandoned room and more like a transparent sea with extremely low traffic. Things still move through it. Forces still operate across it. The material is simply sparse and hard to notice. That hidden traffic is part of what makes void galaxies scientifically rich. Their surroundings look almost bare, yet the galaxy is still embedded in a medium shaped by invisible mass, lingering baryonic matter, and light that has crossed cosmic ages. The void becomes interesting precisely because what remained there is so subtle and yet so important. Even the afterglow of the Big Bang fills those lonely regions. No galaxy is beyond the reach of the cosmic microwave background, the ancient radiation left over from the early universe. That faint afterglow permeates all of space, including the sparsest voids and the dark expanses between their few galaxies. This is a wonderfully humbling fact. A region that feels almost abandoned on the scale of galaxies is still immersed in one of the oldest signals in existence. The emptiness does not block it. The lack of nearby structure does not silence it. The oldest light we can observe still passes through and surrounds those remote systems just as it surrounds us. That gives voids a strange intimacy with cosmic history. They may be poor in present-day matter, yet they remain full of ancient information. A lonely galaxy therefore lives not in silence, but inside a bath of relic radiation that remembers the universe when no galaxies existed at all. Even the deepest hollows are still lit, however faintly, by creation's afterglow. A void galaxy swims in radiation, gravity, and unseen structure. The word isolated can trick us into imagining a galaxy as disconnected from everything beyond its visible stars. In reality, even the loneliest system is immersed in influences it cannot escape. Radiation passes through space from countless sources and from the early universe itself. Gravity links the galaxy to dark matter, distant structures, and the broader evolving geometry of the cosmos. Unseen large-scale features of the web still shape its past and future, even if they are too faint to dominate the local sky. So a void galaxy is not sitting in a blank nothingness. It is suspended in a subtle environment, one made less of bright company and more of hidden context. That is what makes these systems so compelling. Their isolation is visible, but their connectedness is physical. They float in a medium of laws, signals, and invisible scaffolding that never switches off. The galaxy looks alone, yet the universe is still everywhere around it. Its isolation is real, but never absolute. That final nuance may be the most important of all. A void galaxy truly is remote by the standards of large-scale structure. It may have few bright neighbors, sit far from major filaments, and occupy one of the sparsest addresses in the known universe. Yet it is never isolated in the total sense. Gravity still reaches it. Radiation still surrounds it. Dark matter still anchors it. Gas may still flow in faintly across long distances. Even occasional companions can still matter if time is generous enough. The loneliness is genuine, but it exists within a connected universe. That is what makes these galaxies so haunting. They are not cut loose from reality. They are examples of how sparse reality can become while still remaining a single continuous system. A void galaxy is alone enough to feel extraordinary, but not alone enough to escape the larger web of cause and influence. In that tension between remoteness and connection, the whole fascination of the subject quietly lives. Some dwarf galaxies in voids may be especially primitive survivors. Among the most intriguing residents of cosmic voids are the little ones. Dwarf galaxies are small by galactic standards, yet in empty regions they can become scientifically enormous. Because they often grew slowly and avoided the rough treatment common in crowded environments, some may preserve simpler conditions than larger, more transformed systems. Their stars can be fewer, their chemistry less enriched, and their histories easier to untangle. That makes them feel almost like survivors from a quieter chapter of cosmic history. Not unchanged, because nothing in the universe truly stands still, but less overwritten. In a dense cluster, a dwarf can be stripped, stirred, or swallowed. In a void, it may keep more of its original character for longer. That possibility is thrilling. A tiny, faint galaxy adrift in a vast, underfilled region can become a rare witness, carrying clues not because it was powerful, but because it was left alone long enough to remember older ways of being. They can preserve clues to how the earliest galaxies behaved. The first galaxies were not grand spirals with billions of mature stars. They were smaller, rougher, chemically simpler places, built when the universe had far fewer recycled elements to work with. Astronomers cannot watch those earliest systems directly in every detail, so they look for modern galaxies that may echo some of their conditions. Certain void dwarfs are valuable for exactly that reason. They are not ancient fossils frozen in place, yet some may still retain traits that resemble earlier stages of galaxy growth. Lower metallicity, modest mass, and a slower history of star formation can make them useful stand-ins for more primitive behavior. That is part of the fascination. A dim modern galaxy in one of the emptiest regions of space can help scientists imagine how the young universe once built light from simpler ingredients. It is a kind of indirect archaeology, where distance is replaced by isolation and the past is approached through a slower living present. Void galaxies may help explain why some small galaxies stay small. Not every galaxy is destined to become a giant. Some remain modest for billions of years, and voids may help explain why. In a sparse region, a small galaxy may receive less fresh material, suffer fewer mergers, and miss the repeated opportunities for rapid growth that denser environments can provide. That does not mean its life is uneventful. It means the pace of accumulation can stay restrained. A dwarf galaxy in a void might continue forming stars slowly, while never gaining enough mass to transform into something much larger. This makes such systems deeply informative. They reveal that smallness is not always a temporary stage on the way to grandeur. Sometimes it is a long-term outcome, shaped by environment, available fuel, and the absence of cosmic crowding. That idea changes how we think about galactic success. A small galaxy is not necessarily a failed large one. It may be the natural product of a universe that offered just enough matter to begin, but not enough to accelerate. They also test whether missing dwarf galaxies are truly missing. Cosmology predicts many small dark matter halos, more than the number of obvious dwarf galaxies we have traditionally observed. This mismatch is known as part of the missing satellites problem, and voids give the puzzle an especially interesting twist. If tiny galaxies should exist in large numbers, then some ought to appear even in sparse regions. Yet observations have often found fewer than simple expectations suggest. That raises a remarkable question. Are the dwarfs really absent, or are they simply so faint, diffuse, and difficult to detect that we have been overlooking them? Void galaxies sit at the heart of that uncertainty. Each tiny system found in a hollow region becomes part of the larger test of how efficiently dark matter halos turn into visible galaxies. The stakes are high. This is not just about counting faint objects. It is about whether our picture of how structure forms on small scales is complete, or whether the universe is still hiding whole classes of fragile galactic survivors. Some theories predict voids should contain more tiny galaxies than observed. This is one of those tensions that makes astronomy feel wonderfully unfinished. When researchers simulate cosmic structure, the mathematics often suggests that voids should still host a fair number of small dark matter halos. If enough of those halos gather gas and form stars, then more tiny galaxies ought to be visible in the emptiness than astronomers have traditionally counted. Yet the sky has not always cooperated. The observed population can appear thinner than some theories would prefer. That mismatch is not a failure. It is a clue. Maybe the halos exist but stay dark. Maybe star formation is harder to sustain in the smallest systems than expected. Maybe the faintest galaxies are still slipping past our instruments. Or maybe some part of the theory needs refinement. What makes this so exciting is that the emptiest places in the universe become testing grounds for deep cosmological ideas. A shortage of tiny galaxies in a void can ripple outward into questions about matter, feedback, and the basic rules of formation itself. That puzzle makes lonely galaxies important far beyond their numbers. Void galaxies are not numerous compared with the total galactic population, yet their value is vastly larger than a simple head count would suggest. Each one sits at the intersection of major questions about structure formation, dark matter, star formation efficiency, and the influence of environment. A single faint dwarf in the right place can matter because it either confirms a prediction or deepens a discrepancy. That is why astronomers treat these systems with such respect. They are not curiosities collected for atmosphere. They are leverage points in the logic of cosmology. A lonely galaxy in a giant hollow may hold implications for how many unseen halos exist, how gas behaves when matter is sparse, or how galaxies fail to ignite under marginal conditions. In that sense, their importance grows precisely because they are rare and hard to find. When the universe places a visible system in one of its emptiest regions, it is offering a demanding question, and the answer can reach far beyond that one small light. Studying them can challenge our models of cosmic structure. A strong model should not only explain the obvious parts of the universe, it should also survive the awkward cases. Void galaxies are among those cases. They live where the density is low, the growth of structure is weaker, and the expected population of small systems is uncertain. That makes them excellent tests of theory. If simulations predict too many visible galaxies in voids, something may be wrong about how star formation is treated in tiny halos. If they predict too few, then perhaps gas survives and cools more effectively than expected. If the shapes, rotations, or chemical histories do not line up with observation, then our understanding of how environment influences evolution may be incomplete. This is why these remote galaxies matter so much. They push cosmic structure models away from their comfortable middle ground and into a regime where assumptions are easier to expose. In science, that is a gift. The loneliest galaxies can become the sharpest critics of the stories we tell about the universe. They help astronomers ask what the universe builds in peace. Much of galaxy evolution is studied in places where the environment is busy, disruptive, and full of competing influences. That makes it hard to tell what a galaxy becomes on its own and what it becomes because the universe kept interfering. Void galaxies offer a rarer opportunity. They let astronomers ask what structure emerges when the cosmic surroundings are more restrained. Can a small system keep its gas for longer? Can a disk remain cleaner? Can stars continue forming without repeated external jolts? These are elegant questions because they are really questions about nature stripped closer to its baseline. A void does not remove physics. It simply reduces some of the noise. The galaxy still has gravity, gas, dark matter, feedback, and time. What it often has less of is harassment. That makes it possible to study cosmic construction in a calmer setting. These galaxies are not only about loneliness. They're about what the universe is capable of making when it is not constantly interrupted. They also ask what the universe cannot build without crowds. Peace is only half the story. Once astronomers see what galaxies can do in sparse conditions, they can also ask what seems to require busier surroundings. Are certain massive systems rare because voids do not supply enough mergers? Are some kinds of rapid chemical enrichment unlikely without repeated interactions? Do certain structural transformations depend on living in dense traffic? These are powerful questions because they reveal not only the strength of isolation, but its limits. A void galaxy can preserve gas, remain active, and stay structurally elegant, yet it may never experience the dramatic events needed to become something larger or more violently reworked. That contrast teaches us that environment is not just decoration. It can be a generator of possibilities that solitude does not easily provide. In other words, the missing things matter too. A sparse region reveals what growth looks like without a crowd, and by doing so, it shows what kinds of galactic architecture may need a richer and rougher social life to exist at all. In that sense, void galaxies are experiments written across billions of years. Human beings cannot place galaxies in controlled chambers, vary their environments, and watch the results unfold. The universe has done something better, though far slower. It has placed galaxies in crowded clusters, loose groups, filaments, and giant voids, then let them evolve for billions of years under those different conditions. When astronomers compare them, they are reading the results of a natural experiment already performed on the grandest possible scale. Void galaxies are one arm of that experiment, representing evolution under sparse surroundings and reduced disturbance. Their gas, chemistry, shapes, and star formation histories become the evidence. This perspective makes them feel even more extraordinary. They are not merely remote objects sitting in emptiness. They are records of what happened when the universe changed one major variable and then waited an age for the answer. To study them is to examine the outcome of an experiment so vast that no laboratory could contain it, and so slow that only the cosmos could run it. Some of the most isolated galaxies still show bars and spiral arms. A galaxy does not need a bustling neighborhood to become graceful. Even in deep isolation, some systems still develop strong central bars and sweeping spiral arms. That matters because those structures are often associated, at least in part, with interactions or environmental nudges. Yet void galaxies show that internal processes can do a great deal of the sculpting on their own. Rotation, self-gravity, the flow of gas, and instabilities within the disk can all help organize stars into large, visible patterns. There is something deeply satisfying about that. Beauty does not always need a collision to awaken it. Sometimes a galaxy can shape itself from within, drawing long stellar lanes and curved arms through its own patient dynamics. In a void, that result feels even more impressive, because the outside world contributed less obvious pressure. The galaxy became structured not through heavy crowding, but through the quiet mathematics of its own mass, motion, and long, uninterrupted history. That means internal physics can sculpt beauty without many outside triggers. Once bars and spiral arms appear in very isolated galaxies, a larger lesson follows. Galaxies contain enough complexity within themselves to generate striking forms even when external influences are limited. Gas can cool and settle into a rotating disk. Density waves can organize stars into spiral patterns. Central bars can emerge as the inner structure redistributes angular momentum over time. None of that requires a neighboring galaxy to reach in and arrange the scene. This is one of the most elegant messages void galaxies deliver. They prove that cosmic beauty is not always a social phenomenon. It can arise from internal balance, instability, and self-organization acting over immense timescales. That idea is scientifically useful because it helps astronomers separate features that need environmental triggers from features that can emerge naturally. It is also emotionally powerful. A galaxy alone in a great hollow can still become ornate. Left to its own devices, the universe can make patterns of remarkable sophistication without needing a crowd to encourage them. Other void galaxies look oddly youthful for such an ancient universe. The universe is old, yet some remote galaxies seem to wear their age lightly. They can look blue, gas-rich, and still in the middle of making important parts of themselves. Compared with systems in denser environments that have already exhausted more of their fuel and reddened with time, these galaxies can feel unexpectedly fresh. That does not mean they are truly young in an absolute sense. It means their visible state suggests slower maturation. They appear to have delayed some of the transformations that busier galaxies rushed through earlier. This is part of what makes them so enchanting. Inside a cosmos that has had billions of years to grow complex and crowded, a lonely galaxy can still seem caught in a more open-ended chapter of its life. It gives the impression of a system still becoming itself. In the emptiest regions, time has not stopped. But the pace of change can look different enough to make old galaxies appear curiously youthful. Their blue light hints at stars still being born today. Blue light in a galaxy is often a sign of ongoing renewal. Massive young stars burn hot and bright, and for the brief time they live, they tint their surroundings with a color that signals recent star formation. When astronomers see that blue cast in a void galaxy, it becomes especially striking. The system may occupy one of the sparsest large-scale environments known, yet its stellar nurseries have not gone quiet. Gas is still collapsive. New suns are still arriving. The galaxy is not living only on memory. It is actively adding to itself in the present era of the universe. That fact carries an emotional force all its own. A remote island of stars, surrounded by a region where matter is scarce, still finds a way to kindle fresh light. The process is local, intimate, and ongoing. Even in a cosmic hollow, gravity can gather clouds and begin again. Blue light is the visible proof that emptiness has not ended creation there. Some may have swallowed small companions and erased the evidence. A galaxy's past is not always written in obvious scars. Sometimes a remote system may have merged with a faint companion long ago and then quietly smoothed over the event. The smaller galaxy could have been absorbed, its stars dispersed into the halo, its gas mixed into the disk, and its identity lost except for subtle kinematic traces or chemical oddities. In a void, that possibility is especially intriguing because mergers are rarer, and the signs can be easier to miss if the companion was tiny enough. A galaxy that looks serene today may therefore have a hidden history of small meals. That thought adds a layer of mystery to isolation. Even a lonely system may not be as solitary in its biography as it appears in the present. Some of its gas, stars, or structural quirks may be inherited from companions that no longer exist as separate objects. The universe does not always leave dramatic evidence. Sometimes it lets the past dissolve into the body of the survivor. Even in a void, the past can hide inside a halo. A galaxy's halo is one of its most secretive regions. It extends far beyond the bright central disk, holding old stars, dark matter, and sometimes faint traces of ancient interactions. In void galaxies, halos may contain the quiet evidence of events no longer obvious in the visible structure. A small accretion, a subtle stream of stars, or an unusual outer motion can linger there long after the main body looks calm and settled. This makes halos extraordinarily important. They are like the memory field around the brighter, more immediate galaxy we notice first. In crowded regions, the record can become confused by repeated disturbance. In a void, some of those faint traces may survive longer and tell cleaner stories, if only we can detect them. That is the challenge. The past may not announce itself in torn tails or spectacular collisions. It may hide in the outer dark, folded into the halo, waiting for careful observation to reveal that even a very isolated galaxy has not lived an entirely simple life. Every void galaxy marks a place where matter barely won. That may be the most beautiful way to think about these systems. A galaxy in a void is evidence that, in one sparse patch of the universe, gravity managed to gather enough matter to make a lasting, luminous structure, even though the broader region remained deeply underfilled. It is a success, but a marginal one. Nearby places may have gathered too little to build anything visible at all. This gives every void galaxy a special status. It does not merely occupy emptiness. It sits at the threshold between presence and absence, between a region where matter clumped just enough and neighboring regions where it fell short. That tension is part of what makes them so captivating. They are the visible outcomes of almost failure. A few more missing ingredients, a slightly weaker initial concentration, and the galaxy might never have formed. Instead, it shines, quietly declaring that in at least one corner of the cosmic hollow, matter managed to win by the smallest meaningful margin. Around them stretches a darkness shaped by gravity on epic scales. The emptiness around a void galaxy is not random blankness. It is a landscape created by the same force that built the galaxy itself. Gravity pulled matter into richer structures elsewhere, leaving behind immense, underdense basins whose contours reflect the long history of cosmic flow. So the darkness surrounding a remote galaxy has shape, cause, and a story. It is not an absence without structure. It is a hollow carved by matter migrating toward walls, filaments, and clusters over billions of years. This gives the surrounding void a grandeur of its own. The galaxy becomes one visible point inside a much larger gravitational sculpture, a sculpture defined not by what piled up, but by what drained away. When astronomers map such a region, they are effectively revealing the outline of an epic dark terrain. The single galaxy at its center or edge then feels even more astonishing, because it is both part of the sculpture and one of the few lights left to show that the sculpture exists. They prove the universe is not only crowded, but profoundly sparse. Popular images of the cosmos often emphasize abundance. Billions of galaxies, countless stars, immense clusters, and rich glowing nebulae can make the universe seem full everywhere you look. Void galaxies correct that impression. They remind us that the large-scale universe is built as much from scarcity as from richness. Between the bright structures lie vast regions where matter is much thinner and visible galaxies are few. The cosmic web is a pattern of both gathering and absence, both knots and hollows. That truth changes the emotional scale of astronomy. The universe is not a uniform sea of brilliance. It is a mixture of dazzling concentrations and tremendous empty reaches. A void galaxy makes that contrast visible in a single object. It is a luminous system whose very existence points to the immensity of the surrounding sparsity. Through these galaxies, the cosmos reveals one of its deepest design choices. It is not only crowded beyond imagination, it is sparse beyond imagination too. Void galaxies turn cosmic loneliness into one of astronomy's grandest stories. At first glance, loneliness sounds like a minor theme compared with black holes, supernova, or the birth of the universe. Yet void galaxies show how powerful that theme becomes on cosmic scales. Their isolation touches almost everything that makes astronomy profound. It reveals the architecture of the cosmic web. It tests theories of dark matter and structure formation. It changes how gas survives, how stars are born, and how galaxies record their histories. It also stirs the imagination in a way few subjects can. A lone system shining in a giant hollow feels both scientifically precise and emotionally immense. It turns absence into something measurable, beautiful, and deeply consequential. That is why these galaxies linger in the mind. They are not just remote objects in sparse regions. They are the universe demonstrating that emptiness has shape, history, and meaning. Through them, cosmic loneliness stops being a feeling and becomes a grand physical story written across the largest scales of all. As our journey through void galaxies comes to a close, we can leave with a strange and beautiful picture in mind. We've wandered through the largest hollows in the universe, where whole galaxies shine in regions that seem almost abandoned. We've seen that these lonely systems are not empty relics at all, but living places, rich with hidden gas, new stars, dark matter, spiral arms, and the slow work of gravity. We've traced faint threads of the cosmic web, watched matter drain into brighter structures, and found distant islands of light left behind in the vastest cosmic deserts. And there is something calming in that image now. A single galaxy turning softly in an ocean of darkness. Thin streams of gas drifting through the dark. Blue stars kindling where almost nothing else surrounds them. Great voids widening over ages, while small bright systems continue on, patient and unhurried, held together by invisible structure and time. Perhaps that is the feeling to carry with you into sleep. But even in the emptiest places, the universe is never truly empty. There is still motion, still light, still creation, still a story unfolding, slowly and without rush. If you enjoyed this journey through the loneliest galaxies in the cosmos, you might like to subscribe, leave a thought below, or return for another sleepy science adventure soon. And if you happen to still be awake, there should be another video waiting for you on the screen now. ready to carry you a little farther into the wonders of the universe. But for now, let your thoughts grow dim and distant. Let the day drift farther away, and imagine those far-off galaxies turning in the dark, steady and serene as you settle into rest. Sleep well, and good night.